Last time we were talking about the cross product, and we'll continue to talk about the cross product. And then when we explore some applications, there's one major application for the cross product in terms of physics, and that's looking at the torque. But we'll take a look at an application for the dot product as well, and then we'll take a look at the cross product and the dot product as applied to some geometry in math. So we define the dot product, and I would expect that you would practice and be able to compute the cross product accurately with whatever method you're interested in computing it with. So after we do that, then we're going to look at some of the applications. But before we get there, let's take a look at some properties for the cross product. And here we have a handful of properties, much like we had for the dot product. And there's a couple here that we've talked about already. We talked about the idea that the cross product is anti-commutative, which means it's not commutative. You can't just switch the order and expect to get the same answer. But what happens when you do switch the order is that you get the negative of your result. So we saw that geometrically last time. There's a couple of other interesting properties that might be useful for us later on. The second one talks about a scalar being multiplied. I know this probably is not a very good choice of variables that they used. I just copied this from the book. But A, B, and C are vectors, and then you have a scalar C with no arrow on top, so we have to understand that that's not a vector. So this is a scalar C times A. It turns out that you could take that scalar and either multiply the first vector with it or the second vector with it, or multiply the resulting vector product after you take the cross product and then multiply it by C. So that's an interesting way to think about the scalar multiplication within the cross product. The distribution works kind of like the same way it did for the dot product, except since the order does matter, there is a difference whether you cross a single vector with a sum or the sum cross with a single vector. And so that's why there's two different distributions here. The fifth one kind of combines the idea of a cross product and a dot product together. And if you look at the way they reordered things, the order of this cross product and dot product makes a difference. And then the last one was kind of looking at trying to show you the association. Not that I think the cross product's an associative property, but they're not discussing that here. Instead, they're going and revamping this idea of a cross product, and it shows an interesting relationship, another interesting relationship between the cross product and the dot product. So all these can be proven if we assume like A is equal to A1, A2, A3 or something like that, and then you go through the motions of doing some of these proofs. Yeah?
Supposed to be an arrow under the last B on number 4, right?
Oh yeah. Good eye. Maybe I should change that in my notes right away. Whoops. Okay. All right, I suppose we should try to prove one. I don't know which one to prove. They all look pretty hard. We kind of proved the first one already. Let's try to prove the fifth one. So to prove this, what we're going to do is we're going to let A vector, the A vector, equal to A1, A2, and A3. And then we need B and C also, so we'll do the same thing. So we got our vector set up, and basically what we want to do is just follow through the operations. And we can work through it by following through the operations from one side and get to the other side, or some of those proof tricks that you guys might have learned in trig, or even geometry if you remember that far. You can go from either side, you go from both sides, and somewhere in the middle you'll have an equation. So let's do that. Let's take this left-hand side over here, A dot B cross C. So A dot B cross C. And then we'll take our A vector, and then we'll dot it with the product, the vector product of B and C. In that order. So I have B and C up here already kind of on top of each other, so I'm just going to pretend it was an IJK up on top and then do this thing in my head. So in the I direction it'll be B2 C3 minus B3 C2. And then in the J direction, don't forget that there's a negative sign. So whether you put this negative sign or you do the multiplication, again, it's however you want to do it. So it's B1 and C3 minus B3 and C1. And then the last one is B1 C2 minus B2 C1. And then we can multiply this out. The A is equal to A1, A2, and A3. So let's just multiply this out. A1, B1, or B2, C3 minus A1, B3, C2. I think I'm going to distribute the negative sign so I don't have this other negative sign coming out. I don't know which one will work better, but I'm going to distribute the negative sign. So the positive one is the B3C1, and so that's multiplied by A2. And then the last one is multiplied by A3. Okay, so that's half of it. Now, if you can work backwards, that would be great. From here, if you can peel out the A cross B, and then factor out the C3 and stuff, that would be a cool thing to be able to do. But what we're going to do instead is we're going to start here now, and then we're going to try to set them equal to each other. So I'll take this A cross B dotted with C. And then we'll see how that works out. Okay. So let's do A cross B. So A cross B is this cross product of A and B, and again, they're on top of each other already, so I'll just write them out. I'll pretend there's an IJK up on top here, and so we have A2, B3, minus A3, B2, and then we have a negative A1, B3 minus A3, B1. And then our last one is A1, B2 minus A2, B1. And if we dot that with a vector C, it's just these things multiplied with C1 and then C2 and then C3. So A2, B3, C1 minus A3, B2, C1. And then with the negative here, we can change the order. A3, B1, C2 minus A1, B3, C2. And then A1, B2, C3 minus A2, B1, C3. Yeah.
So can you also prove number 5 using bottoms and by 3 vectors?
We could. Did we do that? I don't think we've proven that yet, or I don't think we've stated that property yet. All right. Are they looking alike? How are we going to make them look alike? They don't look alike, huh? Any ideas? I think you need a trick here. The middle term in the last line. So this becomes positive, and then I moved it over here with a positive. There's a trick to this that I'm not remembering. I think you gotta. Any ideas? All right, it's not coming to me, so I don't want to waste too much time on this. I'm going to have to come back to this another time. I'm stuck. So, to be continued. All right. Well, let's move on to an application of the cross product. Did you guys do the cross product lab? Yeah. So, I don't know if you guys heard what Dave said about just prove that it's a volume of parallelepiped, volume spanned by 3 vectors. But this is what this this particular property is saying. So one quick application of this, it's not, I don't know how practical it is, but one quick application of the cross product with the dot product is to find the volume of the vector spanned by, or the volume of, it's called a parallelepiped spanned by 3 vectors. And what parallelepiped is basically like a parallelogram, but it's in 3 dimensions. So not just the sides, but all the faces are all parallel to each other, and then it gets enclosed. And sometimes this is called the triple product, or they call it the scalar triple product. And so imagine 3 vectors in space that are not collinear, which means they're not parallel. If 2 of them are parallel, then you basically have a parallelogram which has no volume. So if 2 of them are parallel, you'll see that you're going to get this thing to equal to 0. And if all 3 of them are parallel, then yeah, it's the same deal. So if you have 3 vectors, what you could do is you can imagine drawing a cube that's been kind of distorted, you know, and edges might be longer than another edge, and then it could be skewed a little bit. So it's not a perfect cube. They're not all right angles, but they do have sides that are all parallel to each other. So this is called a parallelepiped. So the volume of this is given by this triple product. And the proof of this is like the proof of the parallelogram. It'll have something to do with the cross product and the sine of the angle between them and stuff. And then the reason why they put the absolute value here, and we want to think about this as absolute value, is that when you switch the order of the cross product, you might get a negative value. And so what they want to do is they want to just make sure you're getting the positive value out of this. So that's why they put the absolute value there. And then your result is a scalar. So that's why they call it a scalar triple product. So I think, I don't know if we'll do an example of that. But the other application that we need to talk about is application for the cross product as a torque. So here are some pictures. So here's a picture from the book and the explanation. So you can think about the torque as a scalar, but when you look at the torque, it also can be seen as a vector. The torque relative to some sort of origin is defined to be a cross product of the position and the force vectors. And then the magnitude of the torque is going to give you a scalar value that tells you the strength of the force that it's going down. And what we'd like to think about is maybe this the force that you're actually pushing on at the end of that distance vector or position vector is how the force is going to be measured. But what we want to do is we want to think about that as being transposed back to the origin that they're talking about. And then using your right-hand rule, when you do the cross product, we kind of established that last time, that the cross product uses the right-hand rule. If you go from, so I'll do this in another color, from the r vector to the f vector in that direction, then your torque is going to be going in towards whatever the right-hand rule is working towards. Okay. So we could do maybe an example or something. Let's see. I didn't sign in yet. So I think this is section 12.4. You guys only have one of these problems? All right, let's try this one. So bicycle pedal is pushed with a foot with a 60 Newton force as shown. The shaft of the pedal is 22 centimeters long. Find the magnitude of the torque about P. And so this is kind of your origin. This is where the pedal is, and you're pushing down on that pedal. And right now, at this exact point in time, your pedal is 10 degrees to the horizontal, and then you're pushing down 70 degrees to the horizontal. So we can label these as whatever appropriate vectors are needed. So we have the force F pushing down. The distance that we're looking at is r from the origin. So we can imagine that this vector over here is actually a vector coming from the origin. And then now we're kind of interested in this angle, what this angle is supposed to be. So what's that angle? It's what? 80. Now, if we knew the actual vectors themselves, the torque is going to be equal to the distance vector and the force vector, the cross product of the distance and the force vectors. But we don't quite know them. What we do know is we know some information about the magnitudes of these things. I mean, we could probably figure out the direction using the sine and cosine business, and then try to figure out what the force and the distances, the vectors are. But if we know the distance vector and the force vectors, or the magnitudes of them, then we can easily use the formula for the cross product, where we take those two and multiply by the sine of the angle between them. So this, I think, is, what is this, 22 centimeters? And so we're in newtons, right? And newtons is, what's newtons in? It's in meters, so we need to transform the 22 into meters. So 22 centimeters is, what is it, 0.22 or 0.022 or 2.2 or? And the force vector, they gave it to us in newtons already, so 60. So those are the magnitudes that we care about, and then we go to the formula for the torque, the magnitude of the torque, which is just the magnitude of R, magnitude of F, and then sine of the angle between them. And we got 0.22 times 60 times sine of 80 degrees. And whatever that turns out to be. So the distance is already in meters, and then the force is in newtons, and then the sine of the angle has no units, and so this will become Newton meters. Okay? Should we check it? I mean, are we good? What is it? Let's see what they're asking for. Round to 1 decimal, so I guess 13.0. By the way, some of you guys had questions about writing the things in vector form in WebAssign. So if you need to do a vector, there's a little symbol here that says vector. If you click on that and then you type a vector and type in whatever variable you need to type in, that's one way to do a vector. Somebody said they were able to do it using a boldface. I don't know, that worked for some people. It didn't seem to work for others. So if you just want to do a vector as part of your answer in your homework, then make sure you take advantage of these little buttons over here.
Yeah, there's actually an option right there to do bold, because if the people
bold here.
If the people went into a separate text editor and then bolded it and then pasted it, it wouldn't work because this had a special format, these boxes.
So if you press bold and F.
You have to.
Well,
it should bring up a little box.
Yeah. Well, I clicked it, and the box came up, but it disappeared again. But I think if
highlight it and press that.
Yeah. Well, I think this works. So just next time you're looking at things, I guess you got a couple of options for making vectors out of this. You can't just control B for bold, I don't think. You have to actually use one of these buttons on the side. Yeah, it has a special meaning for, I think they actually use Wolfram. They use Mathematica to check your work here.
Special format that is stored in text-wise, so what you see there isn't necessarily what's computed.
Yeah. All right, let's move on to our next section, which is lines and planes. And we will take advantage of the dot product and the cross product in this, and we're actually going to look at lines as if they were parametric equations, and then we'll study them a little bit more. But now we get to look at them in 3 dimensions. And in the next chapter, they're going to be called vector functions. And so there's this kind of this intimate relationship between what we studied in chapter 10 when we talked about parametric equations and what we're going to study in chapter 13 when we talk about vector valued functions. And then here, this is kind of like the first step of putting those two ideas together. And then we're going to talk about, if we have time, we'll talk about planes, and then we're going to talk about distance and using distance formulas of things. So I don't know if we'll get as far as the distance, but I hope to be able to talk about lines and planes, at least the beginning portion of it. Yes, this will be in 3 dimensions. So, find an equation of a line. We know how to find an equation of a line. Usually, back in, pre-calculus or even algebra, you're able to find an equation of a line by having 2 points, and then you look for a point and a slope. So, same idea for lines here, except if you're in 3 dimensions, you can have a well-defined line, and what you would be interested in looking for is a direction vector for your line, and then what you're going to do is you're just going to do a scalar multiplication to hit every single point of that line. And that's how we're going to create our equation of a line. So let's do that first. Oh, just as a little preview, to have a well-defined plane, there's one way to describe a plane, which is what they do in geometry, it seems like. They have 2 points, and then they say that every single point that's equidistant between these 2 points will describe a plane. It's kind of like a weird way to define it, but if you imagine the very midpoint between them is a point, right? If you pick another point that has the same distance between those 2 points, then that'll just be another point. Now imagine an infinite number of those points that's equidistant from those 2 points, and what do you have? You essentially will have a plane. So that's how a plane is technically defined, which is not the best way to define it, but it's a good way to think about it. Caroline? Oh yeah? What was the secret? You factor it out, or you multiply? Because you factor it out because there's none of the factors are in common.
Well, dot product is scale, right? So it's like a bunch of sums. We factor out the A, and then it's the same as the first one.
Oh, okay. No. But show me after class. I'd be interested to see it. Harrison?
Well, I think part of the thing is that I think you're writing the dot product as a vector.
You're writing as a vector, but it's like a sum. It's scale.
Oh. So I did it wrong. Yes, that's true.
So then when you factor the C out, that will be the same as the first.
Okay. Why don't you correct me on that? All right, we'll take a look at it. All right, let's go back to this idea of a plane. So it's a weird way to define a plane, but it turns out that every single point that would be equidistant from 2 other points is going to span your plane. But like I said, that's not the usual way of being able to span the plane. But if you remember with a line, if you have 2 distinct points, then you can draw a line between them, and then that line can extend, right? So a line can be defined by 2 points. A plane, you can think about a plane, it can also be defined by 2 points? No. 3 points. If you have 3 distinct points, then you can define a plane that contains those 3 points, and there will be one and only one plane that would contain these 3 points. And so that's another interesting aspect about a plane. So you can define a line with 2 points, you can define a plane with 3 points, and then how you can find the equation of that is something that we'll eventually be able to do today. And that's going to use the cross product. All right, so let's take a look at a line and 2 points, and we'll see if we can attack these 3 objectives, sub-objectives, with a few examples. So the idea is that if you have 2 points, we'll call them, I don't know, A, B, A1, A2, A3 or something. If you have 2 points, one of the first steps that you need for an equation of a line is a direction, the direction of the line. Which way is this line going to go? So what we could do is we can define this direction vector. We'll call this direction vector D. So we have the points A. I'll call this A. And I'll call this point B. And then we have a direction vector D. So what's D equal to? Yeah? It would be the what? If you were in 2 dimensions, the slope would make sense. But in 3 dimensions, the idea of a slope is kind of strange, because the slope is defined to be just like some 2-dimensional measurement of how high you're going. Yeah? The distance? Close. Yeah, well, no. It's still, the distance formula gives you a scalar, but we actually want to...
If B and A are, capital B and capital A are vectors, then just subtract them.
Yeah. So just subtract them. Remember that if you have points, you can treat them like they were vectors from the origin, and then you can find the difference between them to connect those 2 points, and it's just a head minus a tail. So when we do B minus A, more specifically, we can do the subtraction. So that's very close to the distance that you were talking about, but not quite. So it's B1 minus A1, comma B2 minus A2, comma B3 minus A3. And that's a vector, and those are its components. And that's going to be your direction. So speaking of standard position, let's get ourselves a home, an origin, in 3-dimensional space. And what we want to do is we want to try to attempt to draw this vector. And one way to draw this vector is, well, let's have that vector coming from the origin, and let's start it coming and hitting that point A. So I'm on that line. So the line, by the way, is whatever that line looks like in 3-dimensional space. So I'm at A right now. Now, if I go from A and add D to it, so let me put here that I'm at the point A. I need to use my purple. If I go to point A and add D to it, then I will be at another point on the line. Does that make sense so far? I want to be able to hit every single point on this line. So let me randomly find another point on the line. Like if I take A and add 2D to it, then I would still be on that line. And if I take A and add negative D to it, I would still be on that line. If I take A and add half of D to it, if I take A and subtract half of D to it, if I take A and subtract 2D, I would be somewhere on this line. So what is this shaping up to look like? Or what can I do to generally be able to hit every single point on that line? So if I take A, and it looks like I've been multiplying this by 1, by 2, by 0, by -1, by -1/2. It looks like I can put any scalar value in front of D, add it to A, and I will be exactly on that line. Question? A is a point. We can look at it as a vector. Let me throw an arrow on top of there and then kind of. So this is where I'm going to need to ask you to be flexible with the notation. And when you think about a point, you can think about that as a vector in standard position. Or you can look at it as a point with parentheses, but you know it still works as a vector. That's an important thing to be able to point out. So if we want to use the actual values that we got here, you can think about this as A1, A2, A3 plus T times, and then the D that we found earlier was B1 minus A, B2 minus A2, B1 minus A1, B2 minus A2, and B3 minus A3. Yeah. This is the equation of the line, yeah. This is the vector equation of the line. So actually, if we stay here and call this L for line of T as a function of T, this is sometimes known as the vector equation of the line. So like the lines in 2 dimensions, we need a point and a slope. The line in 3 dimensions, you can think about it as something where you need a point and a direction vector. What we're doing here actually is we're doing that third objective where we're trying to find a 2-point vector equation of the line. So this is a vector equation up here, and then now I'm carrying out the vector manipulation to see if we can look at it from a slightly different point of view. So anyways, if I carry out the vector operations here, I have A plus T times something, or A1 plus T times something, a2 plus t times something. And a3 plus t times something else. I suppose I could have just called this D1, D2, D3 for the directions, but we'll leave it like that for now. So, I think I do want to change it. So just under here, I'm just going to shorten this, D1, D2, and D3. Because that's what D is equal to, right? So you could just mark it under there. Now, these are components along the X, along the Y, and along the Z. And then they have, well, they have a parameter T associated with them. So T is like your variable, your independent variable for a function. So what's to stop us from just calling this X is equal to, Y is equal to, and Z is equal to, right? Looks like it should work out like that. So if we split it up like this, we have our x, y, z as functions of t, and then now it kind of looks like parametric equations. So this is your line written in parametric form. Okay. So the parameter t is, well, it's just a parameter. And sometimes people want to see this equation of the line without the parameter t. And so what you could do is you can solve for t for all of them, and then they would all be equal to t. And if they're all equal to the same thing, then they should all equal to each other. You know what I'm talking about? All right, let's see if I can figure out what I'm talking about. If we solve for t, from all these equations, then they would all be equal to t. Yeah?
Why would we need to solve for t?
Because in some of the exercises that you did in parametric equations, they somehow want you to eliminate the variable t and just write your equation in terms of x and y. So that made sense in 2 dimensions, because now you've lost the parameter t and you just have a Cartesian formula equation with x and y. In 3 dimensions, it's a little trickier, but you can still follow with that same idea, where I can solve for t in all of them, and since all these expressions are all equal to t, I could set them equal to each other and effectively eliminate our parameter t.
So we have a function of x, y,
Not only that, you have x equals something with a y, which is equal to. This is a weird equation because it's now 3 sides to the equation. Yeah. And so if I put this together, and these are all equal to t, let's set them all equal to each other. X minus a1 over d1 is supposed to be equal to t, which is equal to y minus a2 over d2, which is equal to t. So it should be equal to z minus a3 over d3. It turns out that this is called your set of symmetric equations. For the line, and the basic idea here is that now you don't have the parameter t in there. So it's just an equation with x and y and z, but you can't just say in its equation either because it's a 3-sided equation with x, y, and z. So those are the 3 forms of an equation. And let's just see if we could actually do an example from your homework. I probably should stop doing homework stuff. If I do your homework, then you don't get to do homework, and then I'm having all the fun, and you guys aren't having any fun. Let's take a look at this one right here, the first one. Where they didn't give us 2 points, but they gave us a point in a direction, which is what you need. So we want it to pass through this point, and I'm not going to draw the x and y and z axis because that just try to complicate things. So I'm just going to do a random point somewhere in space, and then I'm going to assume that this direction is going in the direction that I want. 1, 3, negative 2/3. So I want the line that's essentially going to be spanned by this. My arrow's a little crooked, huh? So the equation of the line that I want is actually a line passing through that. So the easiest thing to do is to write this in vector form where you have a point and a direction. So let's write this in several ways. L of t is equal to, we can write this point as a vector, or if I get a little careless and write it as a parentheses, it should be understood that it's a vector in this case. So this is the vector form, and then we'd be done, right? And now if we continue doing the vector operation on this, yes?
The point is a vector because we're assuming it's
Yeah.
that's
We're assuming it's like standard position. Yeah. Kind of made it half vector. Okay, let's actually write a vector out of this. And then now, if we do the vector operation, distribute the t, and then add the 2 vectors together, I'll do that in one step. Then each of these components will be the x, y, z of your parametric equation. So if these were equal to your x, your y, and your z, then you can imagine solving for t in each of them, and then you'll have your symmetric equations. Can I do that without having to write the equation? I'm just going to. So I'm solving for t. This will be x minus 8. I'm solving for t. This is going to be y plus 5 divided by 3. And then I'm solving for t. This will be z minus 6 divided by negative 2/3. And then you can do that 3/2 business if you want. But this would be the symmetric equations. Each of these equal to each other would be the parametric equations. And then, of course, your vector equation. Symmetric equations, because there's, I think there's 2 m's in symmetric, yeah. So those are just the ways to describe your line. I have this program out. I think it'd be kind of neat to see how this thing looks like in 3 dimensions. So our point is 8, negative 5, 6. Can't see it, and you have to zoom out. So that's the point. And then we have a vector 1, 3, negative 2/3. If I were to just write that vector out, I would need a 0, 0, 0, 1, 3, negative 2/3. So that's not very helpful. And what I want to do is I want to put this vector and shift it and move it. So I'm going to move it to that point. What's that point again? 8, negative 5, 6. And in this particular program, the way the vectors work is they want you to define the tail and the head. So now I have that vector. Now if I put those lines together in vector form, vector or parametric form, we should see the line passing through that point going in the same direction as that vector. So if I'm just going to steal this, and I'm going to multiply this by t. Actually, I'm going to do this. It needs to be defined as an xyz equals this thing with a t in front of this. What if we make our t go negative? What if I make our t go a little bit past 1? So we see that line now passing through that point and going through that origin. And I think what would be cool is to actually see this being drawn out. So let's see if I could do this. maybe, I don't know if this was the best example because I have a negative 2/3. That's a really small value. So now, if you focus on, let's take away that other vector. If you focus on this red vector is like the drawing vector. It draws out for any value of t that we put in. Right now, t is equal to 0. So if we let t vary, we can see that it's drawing out that vector. Maybe if I freeze it. It'll draw out that vector from the origin. So you can think about that vector function as the tracing vector that would trace out that line. And if you, the way we constructed it, if you specifically had this stop at 0, then it will actually be pointing to that first point on that line that we have. And if you have it equal to 1, then it would be pointing at the second point that we have. And then if you let that t just range from minus infinity to positive infinity, then you would draw every single point on that line. Okay? Yeah. So I think that's the general idea behind lines. Tomorrow, we're meeting tomorrow, right? Tomorrow we're going to talk about planes. If you have a card signed by, make sure your name's on the cards. If you have a card signed by Olivia or Sally, then I'll take that, and then you'll get 1 point extra credit for your next exam. Signed by you. I don't know if that counts. You're not important enough, man. Not yet. Let's make it stacked here. No. But that's a nice try. Thank you.
I was there yesterday, but I thought you meant that they didn't have to sign it just as long as we have this card.
Okay.